Hi, let's take a look at some work with Chapter 11 in a little more detail, primarily focusing on goodness of fit and ANOVA. On homework problem number 1, this is a general conceptual question, an investigator conducting an experiment with 4 treatment groups. She has the response variable as the growth of the plant during an experiment and using an F-test. So your null hypothesis here would be that all 4 treatment groups have the same average growth time. And the alternative would be that at least one group is different. It doesn't necessarily mean that all 4 are different. It means that one group is different. At least one group is different and has a different mean. So that's the option we chose. Now, number 2 is a goodness of fit test. So what I'm going to go ahead and do here is pull up our Statcrunch. I'm just going to shrink this a little bit to the right so you can kind of take a look at how this got set up as we talk our way through the problem. Now, what a goodness of fit test means is that we're trying to measure, did we get what we would expect in the test? If we expected, for example, when we tossed a die that all 6 numbers come up relatively the same, is that what really happened? And that's what this particular problem is kind of similar to. We drilled a hole in a die, we filled it with a lead weight, and rolled it 200 times. So in Statcrunch, we're going to do this in Statcrunch, you're going to enter what are the possible outcomes, that's your first column. The second column is what was observed for each of those outcomes. In other words, for example, there were 37 fours, there were 28 fives. And then we have a column which is the expected value. Now you'll notice they're all the same, 0.167. And that's because 1 out of 6, if all 6 numbers came up evenly, 1 out of 6 is approximately 0.167. You want to use at least 3 decimal places here. The next thing you're going to do then is run the goodness of fit test. So in order to get the goodness of fit results, we're going to click Stat, goodness of fit, chi-square test. We're going to tell it to use the observed column and compare it to our expected values and click compute. Now, when we click compute, we get these results. They're already loaded here for you. I'm going to kind of shrink again so we can look back at the problem. And we're going to notice here that the degrees of freedom is 5. That's correct because there's only 6 possible outcomes, 6 numbers on my die. The chi-squared value is 9.16. But then it asked me to get the critical value. We've done this before, if you recall, back in Chapter 8 and Chapter 7 when we were looking at one sample tests about standard deviation. You would click Stat, Calculator, chi-squared. And this chi-squared calculator would pop up. So you enter your degrees of freedom as 5. Your significance level here is 0.10, so we enter that in, and then we click compute. And so it tells us that the cutoff on the chi-square distribution for the top 10% is this 9.2363569, and you round to the number of decimal places and enter that here. Now, we didn't quite make it past that point. Notice our computed test statistic is 9.16. And the critical value is 9.236. We didn't make it past that point. A different way of looking at that is that our p-value here is 0.1028, and we needed to come under 0.10. So it's really close, but it's not quite. Because of that, we failed to reject HO. Now remember, in a goodness of fit test, your null hypothesis is that it is a good fit, and the alternative hypothesis is that it's not a good fit. In other words, in this case, they appear to be equally likely. The loaded die doesn't appear to have any difference in behavior from the fair die. Now, on the next one here, we're given a little bit of a printout from a TI-8384 calculator here, and we're testing the claim to see if home and visitor wins are independent of the sport. Now, this is your contingency type of test, and you'll notice here you have a rather large p-value. And so we need to think about what does that mean in comparison to the 0.05 level of significance. Fail to reject HO. Let's check our answer. Why do we fail to reject? Because our p-value is so large in comparison to our significance level. What that means is that the null hypothesis, again, recall, was that the home visitor wins are independent. And so if we fail to reject that, there doesn't appear to be any home field advantage. If we did reject HO, what we would be indicating is that there is a home field advantage depending upon the sport. Here's a one-way ANOVA. Now again, this is already calculated for us, so we are interpreting it. So we're looking at a test of weight loss programs, and we had 6 different diets. We had people divided out among those 6 diets and wait a year after starting the diet, and we're testing at the 0.025 significance level if the mean weight loss is the same for all the diets. Now, right away, if you look at your p-value is 0.045379, a little bit less than 0.05. However, it is not less than 0.025, which means we fail to reject HO, and that means we failed to reject the null hypothesis, and the null hypothesis was that all the diets had roughly the same mean weight loss. So should we reject that? No, because the p-value is greater than the significance level. Number 5 is similar. In this particular case, the p-value comes out to be significantly smaller than the significance level. So we fail to we reject HO, because the p-value is significantly less than that level. That would mean, in this particular case, that at least one of those diets had a significantly different mean weight loss than the other ones. At least one of them is significantly different, and you'd have to run some other tests to determine where exactly that difference is. Same thing, number 6, taking a look at results of ANOVA, comparing them. Results, so let's see, our p-value is extremely tiny. This does not mean error. Again, this means scientific notation, so 0.000638. Very, very small p-value, significantly smaller than our significance level, which means we're going to reject HO. And there's sufficient evidence to reject the claim that they are all the same. Number 7, similar type of problem. Use the SPSS results. This is a different type of software. Use these results. Take a look at the significance. The sig in SPSS is similar to p-value, the same thing. So you can use that to compare that to your significance level to determine if it's meaningful or not, and what that tells us in light of our problem. Here's our data. In number 8, we are asked to compare the 3 types of cars for greenhouse gas emissions, and we're testing to see if they all have the same average amount of greenhouse gas emissions. So we're going to copy that right into Statcrunch. Now again, remember the null hypothesis is that they're all the same, and the alternative is at least just one is different, so we could go ahead and check that if we wanted to. But we're going to take a look at computing the Statistic in Statcrunch. So we're going to run a one-way ANOVA. We're going to hold down our control key and hit type A, B, and C. We want those 3 columns compared because there's 3 columns. If there were 4 or 5, we would just continue to do that. And then click compute. And our F statistic is directly located right here. So it says round to 2 decimal places, so we would enter 64.59 and check our work. Now, to find the critical F value, you can simply use your degrees of freedom here, the 2 and 24, go to your F calculator under Stat, and compute that. The p-value then is located here to the right of the F stat, and again, you can enter that in your question as well. Now keep in mind, the p-value here is very small, less than 1/10,000, compared to our significance level in this problem of 5%, which means we would reject HO, and at least one of those vehicles has a significant difference in greenhouse gas emissions. Number 9 is simply a conceptual question, which the following is not a requirement for using a one-way analysis. And I'll let you think about that and do a little bit of reading in the chapter 11, section 4. Again, there is another shorter YouTube video on working with ANOVA on Statcrunch. And recall that you can also use your learning guide. So hopefully those tools are helpful. Good luck.